All right, so far we know a force causes a mass to accelerate. But what exactly are the forces that cause the mass to accelerate? So we're going to go over some different types of forces. So the first type of force is the force of gravity. And another name for that is going to be weight. So that the force of gravity acting on something is going to be the weight of that something. And it's going to be equal to negative mg. Or you could think of it as being equal to mg, but we know that gravity acts downwards, so that this thing here is negative 9.8 meters per second squared. So you could either say that this is going to be equal to negative mg with a positive 9.8, or you can think of it as mg and then substitute negative 9.8 instead of the g. Either way, it's okay. So that's going to be the weight of an object. Depends on gravity. Depends on what planet that you're on. So notice your mass doesn't change. You always have the same mass because you're made of the same atoms. But your weight can change depending on what planet that you're on. The planet is going to determine the gravity that goes into that formula. So I did want to point out a couple of things. One is how to calculate the weight of an object. So that's going to be on the exam. So what is the weight of a 30-gram object? Now notice it's the wrong units, because the official metric unit for mass is always the kilogram. It's like the only metric unit that has a prefix on it. You might think that the official metric unit for mass ought to be the gram, but it's not. It's the kilogram. So the first thing we've got to do is change the mass from 30 grams into kilograms. And then we're looking for the weight, so we're going to multiply it by 9.8. In this case, 9.81 if you go out to 3 significant figures. And then you end up with 0.29, and then the unit. So the unit for force, any kind of force, its unit is always going to be the Newton. So 0.29 newtons. So I wanted you to see that. The other thing I wanted you to notice was in an earlier video, I said that Galileo took a little ball and he took a big ball and he dropped them, and they both hit the ground at the same time. Why? So at the time, couldn't really explain why. Now we can. The little ball is going to have a little mass. The big ball is going to have a big mass. So let's calculate the force acting on each of the two balls. So what I'll do is I'll write force equals little m over here, and then we'll put force over here, and then this is going to be big M, and then it's going to be times A. Okay, so we got force equals ma, force equals ma, so Newton's second law of motion. This is for the little ball, this one's for the big ball. Now instead of the force here, what is the force that is pulling it down? The force of gravity. Do we have a formula for the force of gravity? Yes, we do. So instead of F, let's write down the little m times g is equal to little m times A. And then over here, let's write down big M times G. and that's going to be equal to big M times A. Now, can you see what to do next? Do you notice that both sides have an M? So we're going to cancel the M. We're going to cancel the M. And then what do we end up with? That G is equal to the acceleration that the little ball feels. If we do it over here, we get G is equal to the acceleration that the big ball feels. So they're both being pulled down with the same acceleration. And you should know that if you have the same acceleration, they're going to fall at the same speed, and then they're going to hit the ground at the same time. So this was the experiment that Galileo did with the Leaning Tower of Pisa. Okay, and then another kind of force. So this one was the force of gravity or weight. So let's put this up here. The force of gravity is going to be equal to your weight and is going to be equal to that formula there. So now we want to look at another force that acts in nature, and this one is going to be the force of friction. So the force of friction, what does it depend on? So you notice it's got the G, so friction depends on gravity. You're going to have more friction on a planet that has more gravity. Okay, then it depends on M. So just like this formula depends on M. So the more massive the object, the more it weighs, the more friction it's going to have when you try to push on it. And then the difference, though, is look at here. This one has one more letter called mu. So it's like what a cat does. So mu, it's a Greek letter, and what it represents is the roughness of the two surfaces that are in contact. So you could have a cardboard box, and cardboard has a certain, when on top of carpet, has a certain mu. So that is what that means. It's the roughness of the two surfaces. The larger this thing gets, the more friction you're going to have. If you have something that has zero friction, then this thing would be a zero. Now that doesn't ever happen, but theoretically you could have some kind of a substance that has zero friction, and then its mu would be equal to zero, and then 0 times anything would be equal to 0. And so here is some examples of coefficients of friction. So who cares? So why are we so interested in Newton's second law of motion? Okay, we normally know what the force is. And then we also talked about the force, the electromagnetic force. We talked about the nuclear forces. So normally we know what the force is. We plug it into the formula. We normally know what the object is, so we know what the M is. And then we solve this equation for the acceleration. Once we know what the acceleration is, we've got these equations here. So we've got the how fast equation, the how far equation, and then the hybrid equation. So we could plug the A into those equations, and then we would know how fast is it going, how far is it going. That's the reason why we normally use Newton's second law. So let's take one more break, and when we come back, let's talk about Newton's third law of motion.